Welcome to the One World IAMP Mathematical Physics Seminar. As you know, it's a regular event of the International Association of Mathematical Physics, which is always looking for new members. And today we are happy to have Michele Schiavina from the University of Pavia, who will talk about superselection sectors from Hamiltonian reduction. Please go ahead, Michele.
Thank you. Thank you very much. Thanks to the organizers for, as I said, it's an honor and a pleasure to give this talk to this seminar, which is great. So today, I want to talk about Hamiltonian reduction in the context of gauge field theory. And I want to do it somehow really taking seriously the idea that we are looking at systems where there are local group actions, and we might want to consider quotients by these local group actions to describe the space of physical configurations that are inequivalent. Well, if someone takes this seriously, a number of considerations more or less surprising, depending where you come from, appear, and maybe we can discuss some of these. So let me start by saying that this is a mix of two works that I wrote with Aldo, who is in the audience. Again, so the problem, as I said, is to describe the reduced phase space for a gauge field theory. And you can think of this as some space of physical configurations, meaning that they satisfy certain equations, certain conditions, modulo some group of local symmetries that act on them. And I want to do it in a specific case, which is when your field theory is localized in a region that is a finite region with boundaries and corners. As we will see, this scenario is quite natural and also physical, but it also has interpretation in terms of a more general approach to quantization of field theory on manifolds with higher codimension strata, which goes in the direction of factorial quantization. So this overview is actually an upshot. So if you want, you can just take this and switch off. The idea, so what I'm trying to convey in this talk is that the, say, known or previous Hamiltonian reduction paradigm needs a little amendment when you're working on spacetimes, so finite regions with corners. And this quotient of physical configurations by some gauge, so some group action, factors into two steps, two pieces. Well, two steps rather than pieces. The first step is you can think of as reducing by gauge that lives on the bulk of this finite region. And this is what we call constraint reduction for reasons that will be clear in a moment. And this is going to enforce certain physical equations of motion on our configurations. And if you do this, then you notice that there will be a residual gauge, a residual action. And here, gauge is probably a loaded term, but we're going to talk about this perhaps at the end. We call it flux superselection for two reasons. One is because, well, the relevant quantities that will show up in this stage, they resemble pretty much the case of electrodynamics, where this step is really like taking into account the electric flux. And superselection is a name that is evocative of a large field in algebraic quantum field theory, where it is observed that the phenomenon of quantum superselection appears. our proposal is that perhaps this approach is going to give us a classical version of that. This step is going to tell us that, well, our phase space, the reduced phase space, is going to be subdivided into leaves, and these leaves are going to be labeled by observable quantities. So the expectation that needs to be adjusted because of what I'm going to say today is that the reduced phase space in a gauge field theory is, in general, going to be a Poisson manifold. This Poisson manifold obviously might be singular or stratified, so composed of various smooth strata. But in good cases, this can be described and also quite explicitly. And since it is a Poisson manifold, this is going to be foliated, as I mentioned, by leaves. And these leaves are symplectic. And these are what we call flux superselection sectors. Okay, so and these should be a classical analog of quantum superselection sectors in AQFT. Now, what is interesting is that there are some labels to these leaves, and these are physical, and they are given by Noether charges. And if you look closely at Noether's theorem, I mean, one could argue that we could have known this already back then, but okay, this is true for many things. So these sectors, so these leaves are super selected in the sense that they are identified by Poisson Casimir, so functions in the Poisson algebra that commute with everything, with every other function. And it suggests, because this is, of course, at the level of speculation and perhaps perspective, it suggests that the quantum space of states, whatever that will turn out to be, should be decomposed into sectors or into representations. Okay. I want to focus this application, want to specify this this general picture to the case of Yang-Mills theory, where I select a null hypersurface with boundary. Because this is going to allow us to recover certain aspects of a discussion that appeared, when was it, 10 years ago, perhaps 15 years ago, that somehow identifies certain symmetries as residual. They are called soft symmetries or asymptotic symmetries if you allow this boundary to go to infinity, or large gauge symmetries, depending on the literature piece that you are most familiar with. And well, the upshot is that these are not strange. These are to be expected, and in fact, they are there because of this reduction by stages. So it's fully explained, at least as far as we understand, by this. And we see emerging from our procedure certain concepts that have gone under the name of extended phase spaces, where in the case of Yang-Mills theory, memory, so electromagnetic memory or some non-abelian generalization of that, is treated as a physical label, because that is, in some sense, a Noether charge. I want to mention, because I know that many of you are interested in this case, that unfortunately general relativity, the application of the general relativity encounters many technical and conceptual complications. So this is still, I guess, work in progress, if one can say that, or perhaps again another perspective. So let me begin with, this is still in the introductory part. I want to give you an overview of how I'm thinking about mechanics even, right? So, and the whole point is to understand what is phase space, right? And let's try to use our favorite example, which is just, a particle, a particle with a Lagrangian. So we're considering a variational problem on the space of maps from an interval with boundary to a smooth manifold N into R. And, well, the observation that I'm sure you're all familiar with is that if you take the variation of this Lagrangian, well, this variation will split into something that gives you Euler-Lagrange equations and a boundary term. This boundary term is interpreted as a one form on space of fields. Now, if you actually do restrict this one form to the boundary, what turns out to be is that you can define a space of, let's say, boundary configurations, which turns out to be a symplectic manifold. Symplectic manifold endowed with a symplectic form that is inherited from the Lagrangian problem in the bulk. Here, the bulk is one-dimensional. So we are really thinking of classical mechanics as a one-dimensional field theory on a manifold with boundary. And if you do that, you see that, well, to each boundary component, we associate a symplectic phase space, so to speak, or a symplectic manifold, rather. And one can interpret Hamiltonian evolution as a Lagrangian submanifold of the product of these two symplectic manifolds. Here, for those who are aware of this, one should take the opposite symplectic form on one of the two ends. So, okay, this is simple enough. And as usual, in our practice, we take this as a motivating example to generalize to field theory, which is thought to be, it's just a generalization. But the first thing that happens when you generalize is that, well, you will encounter more general manifolds and intervals. So, for example, we want to look at situations in which we allow cylinders, higher dimensional cylinders, like the one that I drew here, and but also handle bodies or situations where the topology is non-trivial, or where you have multiple connected component to the boundary. So here as well, you will be able, I'll mention something about this later, you will be able to define, at least in good cases, a symplectic space of boundary configurations that you can attach to each boundary component, each connecting component of the boundary. And you will also be able to think of Euler-Lagrange equations as related to a Lagrangian submanifold inside the product of these two symplectic manifolds that you assign to the boundary. Now, if you think of a cylinder, even in higher dimension, as some sort of time evolution, although you don't really need to do that, but it's one interpretation. If you look at generic three-manifold or a higher dimensional manifold, this will, in principle, have a different interpretation. So in this case, you can decorate two of these boundary components as incoming, and one is going to be outgoing. This is obviously non-canonical, so there is something to be understood there. And you can give this a more general interpretation in terms of like groups or groupoids. And if we're thinking about quantum theory, you're going from an interpretation in terms of evolution operators from the state that you assign to a boundary component to a state that you assign to another boundary component, to something more general, which could be a multiplication in this case, or a co-multiplication, or something more complicated. Now, here I have written the C indexed by connected component sigma I. And this encodes Cauchy data. So as we know well, at least in gauge field theory, you cannot expect every field configuration on a Cauchy surface to be extendable in the interior, but you need to satisfy certain constraints, certain additional conditions that come from the equation of motion. So this data is encoded by a submanifold that in good cases is coisotropic inside this symplectic manifold. And that's where the, say, usual Hamiltonian reduction paradigm comes into play. I will talk about this in a moment. But you can also do something even more complicated, and you can look at, for example, a physical scenario where you are in some Minkowski spacetime and you isolate a region which is finite and is obtained by intersecting two truncated cones, for example. So in the situation like this, you see that you have several boundary components. You can mark several boundary components, and you will have space-like boundary components, and you will have null boundary components. And at the intersection of these, you can identify what we call corner. So a codimension 2 hypersurface that is marked for some reason. And the question here that I'm trying to address, and Aldo and I have been trying to address for a while now, is what is the role of these corners and how you should treat them and how do they modify the previous discussion. Okay, so that's all for the introduction. I am going to introduce some of the tools that we're going to use. So I cannot assume that you're all familiar with what Hamiltonian reduction is. So let's try with a simple example. We begin with a just simple symplectic manifold. You can think of R2n if you're more familiar with that. And this comes equipped with a symplectic form. And we want to give a Lie algebra action data on this manifold, which means I want a Lie algebra morphism between our chosen Lie algebra fracture G to vector fields on the manifold. Fundamental vector fields are the image of this action map of a basis of the Lie algebra, for example. I call them with a little hat. And the statement that this is a Lie algebra morphism means that you can intertwine Lie brackets using rho. Another way of saying this is that if you take the bracket of two fundamental vector fields, you will get another fundamental vector field multiplied by the structure functions, or sorry, structure constants of this Lie algebra. Since we are on a symplectic manifold, it makes sense to ask whether there is compatibility between these fundamental vector fields and the symplectic data. And one particular interesting compatibility condition is that such fundamental vector fields are Hamiltonian, which means that for every A, there is a function HA, and contracting the fundamental vector field with the symplectic form, I get the differential of this function HA. Another way of saying this, if you're more familiar with this, is that the fundamental vector fields can be written as the Poisson bracket with this function HA. So it's a derivation, Poisson bracket is a biderivation, so everything makes sense. In this case, we talk of, we say that we have a Hamiltonian G space. And an equivalent way of saying this, which well, is what we're going to use later on, is that there exists a momentum map, which is essentially a collective function for all of these functions HA, which I think of as a function from M to the dual of the Lie algebra that takes an element in the Lie algebra and gives me this combination of HA at the point X paired with psi A. Here, I am saying this for completeness. We're not going to be concerned too much about this concept, but equivariance for us here, well, this is infinitesimal equivariance, but it's a statement that, well, if I act with the Lie derivative of fundamental vector field on H and then I pair, that's the same as taking the pairing of H with the adjoint action on the Lie algebra. And if that's not the case, then one can show that the failure of this is a cocycle in the algebra cohomology, which has an extension of this picture, which I'm not going to talk about. So let's look at some examples. I'm going to think of M now as the cotangent bundle of Rn for real. So this is R2n. And I'm thinking about two actions. One is the action of Rn, and one is the action of SON, the Lie algebra. And these are the fundamental vector fields given elements V and O inside the Lie algebra. And so what one can discover with a quick calculation is that the momentum maps associated to these two actions, well, they exist, and they are given by simply the linear momentum, so Pi, thought of as an element of the dual of the Lie algebra Rn, or the angular momentum, which is written here in a perhaps not so recognizable way, again thought of as an element in the dual of the Lie algebra SON dual. It takes an element O and spits out a number. Why is this really the angular momentum? Well, if you are in dimension 3 and you identify SO3 with R3 using this explicit map, where now OK is, this guy is just a vector in R3, you can see that, well, the angular momentum function can be rewritten as the cross product of Q times P, where you're thinking of this as an element in the dual of the Lie algebra, okay, using these identifications multiple times. Okay, so this is exactly, I mean, this is a familiar example. We've seen this, and one can phrase this example in the language of Hamiltonian momentum maps. Another element that I'm going to need is the following observation, which is that, well, if you take the algebra, you can take its dual, and this is a linear Poisson manifold where I can write down the Poisson bivector in the following way explicitly, where F, A, B, C are the structure constants of the Lie algebra. XC is the coordinate on the dual of the Lie algebra. This tells me that the Poisson bivector is linear. Another way of saying this is that on coordinate functions, I get this Poisson bracket, which is obtained from the Poisson bivector in the following way. So this Poisson manifold, as all Poisson manifolds, is foliated by symplectic leaves, and the symplectic leaves here are coadjoint orbits. So on the dual of the Lie algebra, there is an action of the D group, and that is too fast. There is an action of the D group, and the action is the coadjoint action. As you can see, you can identify an orbit. So these are points in the dual of the Lie algebra that are obtained by mu via coadjoint action. These are all symplectic manifolds. And this serves as a prototype for all symplectic manifolds. Any Poisson manifold. Any Poisson manifold is indeed foliated by symplectic leaves. And these leaves are labeled by a choice of values of a complete set of Casimir functions, so functions in the Poisson algebra that commute with everything. So given this, we are going to state a theorem, or a collection of several theorems, rather, that if you have a free and proper Hamiltonian action on a symplectic manifold, and we assume that H is equivariant, given any coadjoint orbit, this constructs for you a symplectic manifold, which is obtained by taking the pre-image of the entire coadjoint orbit for a point mu and quotienting by the group. For example, you could take the zero-level set of the momentum map and quotient by the group, or you can take any other coadjoint orbit. And I'm putting both examples here because both will be relevant later on. So another way of saying this is that the quotient of M over G, remind you that the action is free and proper, so the quotient is smooth, is a Poisson manifold. And the symplectic leaves of this Poisson manifold are exactly these symplectic manifolds that I constructed before. Here, modulo connected components, right? So here there may be something hiding somewhere. Okay, this gives me a symplectic foliation of my Poisson manifold. And again, I have that these orbits are a model for what I call a sector, which is the pre-image of a coadjoint orbit modulo G. Okay, so this inclusion, this embedding, it's actually immersion, is a model for this immersion here. So for example, if you take the cotangent bundle of Rn, you remove the zero for regularity purposes and quotient out by the action of SON, well, you will have some stabilizers, but this can be resolved. This will give you a Poisson manifold that is foliated by leaves with fixed angular momentum. Okay, so this is going to be essentially what happens in field theory, but with a twist. And the twist is the following. Now, consider that you are given a normal subgroup G naught inside G. And this to this you can associate a momentum map. And because of this, you can consider the reduction at zero. Okay, so here I am deliberately choosing to only consider reduction at zero for this normal subgroup, and this we will see is motivated by physics. So I'm considering the reduction at zero here. And then the theorem is that, well, then there will be a residual Hamiltonian action of the quotient group on this reduction at zero. Okay, so just because I have a normal subgroup, I get all of the structure sort of for free, up to regularity issues, obviously. And this comes with a momentum map, which I call H underline, that can be characterized in this way. Now, the interesting part of this is that, well, we know, because of the previous theorem, that the first stage, so the reduction at zero of the normal subgroup, is a symplectic manifold. And this symplectic manifold has a Hamiltonian action on top. And the second step, so when I reduce twice and I take the remainder of the Hamiltonian action by G underline, this is going to be Poisson. So the second stage reduction is just a Poisson manifold because the general theorem says so, possibly singular. And this is foliated by these sectors that are obtained by taking pre-images of coadjoint orbits of the residual group. Okay, So this is a structure that I want to consider. It's not clear yet why I want to consider this in particular, but if we can apply this to our physical scenario, this is what we get. So let's see what is the scenario now. So I'm going back to a Lagrangian field theory that for simplicity now I'm going to consider defined on a cylinder obtained by crossing a surface sigma with a closed interval 0, 1. Now, if sigma has a boundary, you can imagine that I will have a marked hypersurface of codimension 2, which I call a corner. So the corner is given by the boundary of sigma at 0 and the boundary of sigma at 1. Okay, so I will have some space of fields over this manifold, and I will have a local Lagrangian form, which I think of as a top form valued functional over my fields. And it is a, well, general results by Takens and other people in that period, including Zuckerman. But I think that this is actually due to Takens. That the variation now, this, the variation of this Lagrangian density splits into a term that contains other Lagrange equations and a piece that is the exact. So when you integrate, it's going to give you a one form on sigma. So if you follow this procedure, you realize that it is possible, at least in good cases, to induce some symplectic phase space on configurations on sigma. We call this the geometric phase space because at this stage I'm not seeing any equations of motion, so I don't see any physical requirements on my configurations. And if I want to induce that requirement, so if I want to look at the equations of motion, well, this procedure tells me that there will be some subset of this induced phase space on sigma that is going to tell me what the Cauchy data is. So for regularity, I want to apply our method, we need to assume that the gauge symmetries are nice in the following sense, that if I start from a group action on this space of fields on the whole manifold M, I can induce a group action on the manifold P that I assign to sigma. This is a restrictive assumption because while this is going to work fairly well for most, let's say, regular, normal, standard gauge theories where the gauge symmetry is internal in some sense, this is going to fail for general relativity. And this is actually the diverting point at this stage for us. Okay, so we're going to assume that we have a locally group action on this symplectic manifold that I assign to sigma, which is a codimension 1 hypersurface in my spacetime. Okay, so here is the full axiomatic picture. In the previous slide, I told you how it comes from, let's say, a Lagrangian field theory in the usual sense. But if you are unsure of that, you can just take this as an axiomatics. So what I want is a locally Hamiltonian G space. So I want P to be modeled by sections of a vector bundle over sigma. and I want to have a local Lie algebra action on this space of fields. In order to make this space symplectic, I do it by saying that I have a symplectic density. And the symplectic density is a closed two-form on this space of fields, whose integral is weakly non-degenerate, meaning that it's injective when you take its map to the cotangent. So this is, generally speaking, the best you can do in field theory. And there are many examples where this actually works. Now I generalize the concept of Hamiltonian momentum map to the case where, well, I'm doing everything sort of point-wise, or say density-wise. So for me now, H is no longer a function from fields to the dual of the Lie algebra, but it's something slightly more general. It's a density of that. So I'm taking a functional on fields with values in a top form on sigma, with values in G star, or maybe this could be said better. Okay, so this is the object, and I wanted to satisfy a densitized version of the condition I had before. I mean, formally, it's exactly the same as we had before, but here you just need to be careful that these objects are densities, and so this condition holds pointwise. The fact that this holds pointwise is important because it is a bad habit, I think, in studying gauge theories, to think that we can integrate by parts for free. And in fact, we cannot, at least not always. So here, this means that this condition holds pointwise, which means without integrating by parts, if you want to be really concrete. And again, I have a generalization of the notion of equivariance that works, again, pointwise for this particular scenario. And I also have a notion of equivariance that I want to be satisfied up to the exact densities. So why do I say that integrating by parts is not for free? It's because this pairing between the variation of this Hamiltonian density and psi may in fact depend on higher derivatives of the section of the vector bundle psi. Remember the psi, this guy here is a section of a vector bundle. So hidden inside this expression, which is very compact and elegant and whatever, but it hides the fact that I may be taking derivatives of this function with values in the Lie algebra side. And so here, integrating by parts is a relevant step that I might not want to do. Another way of saying this is that this pairing is generally not infinity sigma linear in the entry side. Okay, it's going to be R linear, but not infinity sigma linear. The connection with the previous picture comes about when I integrate both the symplectic density omega and the Hamiltonian density H on the hypersurface sigma. This I can do because structurally I'm saying exactly this, that this omega is a 2, top form and H is a 0, top form, so I can integrate them over sigma. Okay, and if this happens, well, I will have an equivariant momentum map for the action of the Lie algebra or the Lie group. Good. Are there any questions so far? Yeah. Good. So if the boundary of this surface sigma is empty, we can recover physical configurations on P as the vanishing locus of Noether's current, which in good case is going to be exactly this H. Okay, so here I'm merging a bit two concepts. So Noether theorem is going to tell me that H is the exact on shell. Okay, this is Noether's theorem. And if the boundary is empty, this is the same as asking that the integral of the density H must vanish. So if then H is a momentum map, we know that physical configurations are the zero-level set of the integral of this Noether current. This is going to be our constraint set, and the reduced phase space is going to be the Hamiltonian reduction at level set 0. Remember what I did before with 0. So level set of 0 modulo the gauge group. And again, in this case, this is the reduced phase space of the theory, and it is a symplectic manifold. But I have assumed that the boundary of sigma was empty. If I have a corner, so if the boundary of sigma is no longer empty, you can check very easily in examples or just by taking seriously Noether's theorem that the level set, the zero level set of the integral of the Noether current is no longer the correct locus, is not the correct physical locus anymore, because setting H to 0 everywhere, including the boundary, is going to set some corner conditions that I might want to control. And our way around is to actually show that, in fact, there is a natural decomposition of this momentum density into H naught and an exact term. And in fact, physical configurations following Noether's theorem are given by the zero-level set of this bulk component of the Noether current. Okay. So a little terminology, we call H naught the constraint form because it's going to tell us what the constraints of the theory are. And dH is the flux form because it's going to tell us what the fluxes are. So I'm going to give you an example. The example is Yang-Mills theory, where I take three-dimensional hypersurface sigma inside, let's say, Minkowski spacetime, and I look at, well, inside a cylinder, which is actually, no, sorry, sigma is a codimension 1 hypersurface inside Yang-Mills, but I want sigma to be a manifold with boundary. Okay, so sigma has the structure of, for example, a sphere, a two-sphere cross an interval, closed interval. So sigma is a manifold with boundary, and it is embedded inside four-dimensional Lorentzian manifold. So this is null because we're thinking of sigma as a null hypersurface inside Minkowski space, for example. Okay, so I have a way to write the gauge field and the electric fields using this decomposition of sigma into an interval piece and something else. And I can write down the geometric phase space, which is induced by Yang-Mills theory in the Lorentzian manifold, as the following data. So this is, well, this manifold defined here with this symplectic form. Okay, you can check that this is actually symplectic. And I have the usual action of gauge transformations on my connection forms A, given by just gauge transformation here, and the adjoint action over the electric fields, generalized electric fields. And it is possible to show that, in fact, this action is locally Hamiltonian, and that this local Hamiltonian density splits into something that is called H0 and something that is the exact. And this H0 contains this term G, which is nothing but a version of the Gauss constraint in these variables. Okay, so nothing strange here. It's what you would expect. It's just that the parametrization is slightly different, so we have to introduce all of these variables. Okay, so again, we see, as expected, that the Gauss constraint is the zero-level set of H0 and not of the full Noether current, because otherwise I would have to set to zero also these terms. So, very well. The problem is that H0 is not a momentum form, locally a momentum form, for the whole gauge group anymore. And if you remember where I started, I said, well, I would like to find a subgroup which is normal. Here's where that picture becomes applicable. Can I find a subgroup such that this constraint set is exactly the zero-level set of the induced momentum map for the action of this subgroup? The answer is yes. There always is a maximal Lie ideal if you're thinking about the algebras or normal subgroup, such that the associated momentum map is constraining, so it vanishes exactly at the constraint set, which is the physical data of our theory. We call this the constraint gauge group. And because it's normal, we have a quotient group, which we call the flux gauge group, exactly as before. But then applying the previous theorem, we have that there is a residual Hamiltonian action well, obviously assuming that the first reduction is smooth, there is a residual Hamiltonian action over it. And now the momentum map, the small h, is indeed related to this flux form. Okay, so here one has to be careful about these relations, but what we're saying is that nothing is thrown away from the Noether current. The bulk part of the Noether current is going to reduce first stage, and the second part is going to give me a residual Hamiltonian action. Okay, so now C underlined, which is again the reduction of the zero-level set of the constraint form by this constraint gauge group, is a symplectic space, but we have a residual action. Let me repeat myself. We have first stage is a Hamiltonian G space when smooth, obviously. And then I can do exactly like I did before. I can consider the coadjoint orbits of the residual gauge group. And I can construct these sectors by taking the pre-image of these coadjoint orbits and quotient by the group. Each of these is going to be symplectic, and their union is going to be Poisson. So, if I'm interested in physical configurations modulo all gauge, all the action of the whole gauge group, then the answer is that this space is going to be Poisson. There's nothing, there's no way around this. And this Poisson space is, by standard arguments, foliated by these superselection sectors, which are the pre-images of essentially the neutral charge of these cojoint orbits. So let me go back to Null-Yang-Mills theory and try to see what we can extract from this. I'm running a little late, so I want to tell you a little bit of a story about Null-Yang-Mills theory, which is that, let me reveal all this slide. We started from here. We started from this symplectic space, which was induced by Yang-Mills theory on a four-manifold. And in the literature, you can find several proposals for a reduced phase space for Null-Yang-Mills theory. The original proposal was by Arsteker and Streubel, where it was said, well, actually, this is what it is, right? Right now seems a little bit arbitrary, but we'll see why. And later, well, some other people started saying, well, perhaps this is too small, and we actually need to extend it, either by adding some gauge group or some Lie algebra, right? So the cotangent bundle of the group or the Lie algebra. So it seems a little bit confusing because now nobody really understands which one is the real reduced phase space and in what sense. The original observation that led Arsteker and Streubel come up with their space is that, well, if you gauge fix one of the fields, the A field in the interval direction, well, using this procedure, this is what you get, right? So if you gauge fix by setting to 0 the gauge field along U, you get precisely this symplectic space. Okay. Then later it was realized that, well, actually, if you take that as a symplectic space, that should be the reduced phase space, you have some spurious large gauge symmetries that are still surviving. There's still something. Well, the idea was that, well, if the Arsteker-Streubel phase space is the reduced phase space, then these are some sort of new symmetries that are maybe physical even, and they were called soft symmetries because of the relation to Weinberg's soft theorems, and their conservation laws were interpreted as word identities and as the soft theorems themselves. So what is the meaning of this, right? Can we say something about this plethora of reduced phase spaces that appear in this field? And I think the answer is yes, because of the following. So if you look at the case that I outlined before, up to some details that I'm going to swipe under the rug very happily, you can identify, you can see that the constraint gauge group is nothing but gauge transformation that vanish at the boundary. And the residual gauge group is two copies of gauge transformations at the two endpoints, at the two spheres, celestial spheres, if you want. So if you do a little trick of parametrization of vector value fields or sections over this manifold, so that an element inside this Lie algebra can be rewritten as, well, the difference of its values at the final initial endpoint and one of the two, for example, the final. You have that the flux map, unreduced, just looks like this. You can see that the flux map is really associated to the electric flux in some sense, right? So this is the electric flux across one of these corner components. Well, what we managed to show with Aldo is that, in fact, the first stage of the reduction by stages that one should do to describe this reduced phase space is nothing but this extended Ashtekar-Streubel phase space. Okay, so it kind of makes sense, right? It's a bit larger than the Ashtekar-Streubel phase space. And this is what you get naturally from symplectic reduction of a piece of the gauge group, a subgroup of the gauge group. Well, but then because of this general procedure, general structure, we have a residual Hamiltonian action of two copies of the algebra valued functions over the spheres, the endpoint spheres. It's very explicit. This is how it looks like. And this is the momentum map. And you can see, I don't know if you have stumbled upon this before, but you can see that this piece in particular, well, okay, this is just the value of the electric field at, I think, Aldo, correct me if I'm wrong, but this should be the initial, yeah, okay, one of the two. And this is what? This is called electromagnetic memory in the literature. So the electromagnetic memory, here I'm referring to several people who worked on this and are opinionated about this, is a component of the momentum map, of this residual momentum map for the action of these two copies on the linearly extended Ashtekar-Streubel phase space, which for us is just the first stage. So note that since the residual gauge group here is the direct product of two groups and the actions commute, we can proceed by stages again. And this, I mean, we did this just to explain why one gets the Ashtekar-Streubel phase space, but okay. So sort of an intermediate result here is that if you take the first stage and you reduce with respect to only one of the two copies at the momentum map, the zero level set of the momentum map given by the electric field, this gives you the Ashtekar-Streubel phase space. Okay, so what was thought to be the true reduced phase space of Null-Yang-Mills theory ends up showing up, at least in our approach, as some intermediate second stage reduction of a larger process. Because it's not yet the full thing, because we are only quotienting by one of the two copies, it still has a residual Lie algebra action. And this is exactly the Lie algebra action that was called soft symmetry. It's this notion that, well, on the Ashtekar-Streubel phase space, there is still something. And the momentum map for this residual action is the electromagnetic memory. Okay. So I'm just gonna tell you just very briefly that this can be done in the non-abelian case as well. I apologize, I probably should have said that all of this works for the abelian case. In the non-abelian case, something can be said, and you have a very similar result. You have that on the Ashtekar-Streubel phase space for the non-abelian Yang-Mills theory, you still have a momentum map, and this is given by this generalization of the memory observed. Okay, let me conclude. Okay, so this is something that will anger Eli. Sorry, you've seen this already. Apologize. But so how do we think of this in terms of quantization? Very quickly, this is the classical structure. Okay, on the left column is the classical structure in the level of functions. Okay, so if we have some sort of representation or something that wants to go in that direction for the Poisson algebra of functions on C underline, I can induce a representation for functions, so invariant functions, so functions on the fully reduced phase space. And now the trick is that this algebra has a center. If this algebra has a center, it is expectable, at least, that this will induce some sort of decomposition of whatever Hilbert space I am representing this algebra on in terms of irreducible representations of the space of this algebra. Okay, so I'm going to conclude saying that in good cases, Noether theorems, really as back as that, set us up for Hamiltonian reduction. And our proposal, I guess, is that the reduced phase space should be taken seriously as the zero level set of the Noether current in the bulk, quotiented by the entirety of the gauge group. And if you do this in the presence of corners, the best thing you can do is to say that this space is Poisson. And this gives you this very explicit structure where you are really reducing in stages to get to the final symplectic leaves. And these symplectic leaves are labeled by a fixed value of the electromagnetic memory. And so, in some sense, quantization at E equals 0 should yield a decomposition in memory representations of whatever the space of states ends up being. And this is simply a consequence of the Hamiltonian structure of the problem. Thank you.
So thank you very much for this interesting talk. Are there any questions or remarks?
Eli, are you upset with Michele?
I think Dan has a question.
I'll let it pass.
Hi, Michele. I don't know if
Yes.
you can. I don't know if you can hear me,
I
but
can.
somehow my camera is not starting. But there we go. Well, first of all, thank you very much for the talk. Very, very nice. I had a question about the fact that if you have corners in your manifold, there's some ambiguities to the symplectic form usually, because, well, essentially your symplectic potential is only given up to an exact form.
It's true.
How does is there, because you did have some assumptions, of course, on what kind of symplectic form you have. Does that in any way constrain these ambiguities, or is there a way that
some ambiguities are less relevant than others. I'm going to say that in short, I cannot prove that these ambiguities are not fully relevant yet.
Okay.
But I highly suspect that they are irrelevant, but in perhaps a way that you might not be fully happy with. The way I think about this is that there should be some sort of L-infinity cohomology hiding behind all of this. And then from that point of view, changing that representative should not matter.
Yeah.
The issue is well, the variational bicomplex has a lot of structure in terms of acyclicity, and there exist homotopies by which you can choose primitives of these the exact forms, right? So if you really want to do it correctly, you have to incorporate the homotopies in your prescription.
Mm-hmm.
So you will have some maps that do that.
Yeah.
And so the structure you will get will depend on these homotopies, but it will depend sort of in a coherent way, consistent way. So,
and of course, it should not, it should not affect the global physics in a sense, but
that's what I'm thinking. That's what I'm thinking. But
yeah.
I don't even have like a good example where I can show you that indeed this doesn't matter. I have some roundabout ways in which I can argue my way out of that. But so, for example, if you were to embed all of this stuff in the Batalin-Minkowski formalism, where everything now is cohomological, there you show that, okay, to a Lagrangian field theory, you assign a tower of things, of local forms that are essentially the primitives in codimension 1, codimension 2 of the various objects. That, of course, is a choice, right? But you can show that if you change that choice, the global structure of the theory doesn't change, of this BV theory with boundaries and so on. Meaning that that change should be equal to a choice of a representative of a cohomology class. So I can show you a little bit of that, not now, but I don't have a proof of this hunch.
Yeah. Well, thank you very much for thanks.
Okay, any other questions? Okay, so my question would be, is it possible to explain how this formalism relates to what we know from textbooks, like Dirac bracket formalism, for example?
Yes, so the relationship with the Dirac bracket exists, but I think primarily in Alberto Cattaneo head, because I've heard him say it. So it's not written explicitly anywhere.
It's not open access, I'm afraid.
No, but under invitation, perhaps this could be. But no, I mean there is, in fact, I think a nice. I mean, he has a nice geometric understanding of exactly the relationship between the Dirac bracket and this picture, which, by the way, it was written on the slides, but it's after Kijovsky and Tulchiev. This construction of the geometric phase space was done by them, was suggested by them, and we just use that to work in terms of group actions on top. I think, but again, I cannot prove it to you right away. I think that the upshot is that Dirac's approach works in some cases equivalent, but it is restrictive and perhaps even unnecessarily cumbersome in certain ways. I think that we can reproduce most of what is known, what was known using Dirac brackets, and some. So, and in a shorter time span. So I really do think that that there is some advantage in changing the perspective there a little bit.
Okay. Then following up on this question about textbooks. Another thing we find in textbooks, Gupta-Bloiler type quantization of theories with constraints. So that's maybe a question about this last slide about quantization. When you, let's say, vaguely, if you quantize, do you expect a theory on a Hilbert space or on a Krein space?
Oh, yeah. Okay, yeah. So, right. I guess ultimately, well, I don't know. No, okay. So again, I don't have an answer to this because generally speaking, when I quantize, or let's say I'm thinking about quantization of the stuff, is not directly by let's say geometric quantization of these reduced spaces, right? That is difficult. So what I'm thinking instead is more along the lines of cohomological or BFV quantization. And there, well, the quantization is typically done of a cotangent bundle then, which is easier. But it's a graded cotangent bundle, and so you will certainly have states of, let's say, 0 negative norm. Okay, so that's not going to be a Hilbert space for sure. Now, I think that in the original papers, they claim that when you take the cohomology, so you will get some quantum complex that quantizes your classical BFV complex. You get something, and they claim that when you take the 0th cohomology of that complex, you get something that could have a Hilbert space structure, but I don't know. I mean, that is hard.
Okay.
But okay, so this is don't quote me too much on this. I mean, I'm being recorded, so that's a problem. But let's say, if you ask me, I don't want to necessarily restrict myself to looking at Hilbert spaces. Okay, so whatever works.
Okay, thanks. So any other questions or remarks?
So let me perhaps just add a little comment, if you allow me.
Sure.
So this very vague heuristics, I mean, it's true, it's very vague, but we can sort of see traces of this in known topological examples. So for example, if you're thinking about Chern-Simons theory, thinking about Chern-Simons theory, there it's reasonably established that when you take this fully reduced phase space, you will get some sort of foliation by coadjoint orbits of the loop group in some sense. And then taking integral or quantizing these orbits will give you representations of the loop group. And now, whether that is a decomposition of a larger vector space is something I don't know. But in those examples, so Chern-Simons theory, BF theory in 2 dimensions, this fully reduced phase space is simple enough that maybe some classic techniques of quantizations could work. And this is perhaps the advantage of really looking at this space of configurations on manifolds with corners, because you are reducing the dimension by 2. Right? So if you start from a 2D theory, you will get a 0D theory, and so you will get a finite dimensional something, Poisson manifold, at least in principle. And so then you have a finite dimensional Poisson manifold, and then you can hope a little bit more.
Oh, okay. Okay. So any other questions? Does not seem to be the case. So maybe let's thank Michele again.